Okay, well, maybe we'll get started. So it's a pleasure to welcome Ilya back to Caltech. We were just noticing that half of his candidacy and defense committee is in the audience or up front. So Ilya is a long distance cyclist, a hiker, mountain rescue team member. He's on his way to go skiing in Aspen, but he's a board member of the Aspen Center for Physics. So if you too want to go skiing in Aspen, you can chat him up for your favorite program ideas, so you have an excuse to go skiing in Aspen too. So Ilya got his undergraduate degree in physics at Stanford in 2000, and his master's degree in computer science at Stanford in the next year. While he was at Stanford, he got into relativity by working on the infamous Stanford gyro experiment, or GPV. And after a year in computer science, he decided, I guess, that physics was actually more fun, so he came to Caltech and did his PhD with Kip Thorne on titles The Three F's of Gravitational Wave Astronomy: Sources, Signals, and Searches, covering intermediate mass black holes, extreme mass ratio mean spirals on non-GR lumpy black holes, periodic standing wave approximation for heavy ingoing as well as outgoing waves, deep orbit circular, LISA searches, and so on. Then he spent, I guess, 4 years as a postdoc at Northwestern and a year at MIT and a NSF fellowship. Then in 2011, he moved to Birmingham, the real Birmingham, UK, not Alabama, and rose through the ranks from lecturer to full professor. And then just in time for COVID-19, he decided to move to Australia, where he's a professor at Monash University, and a future fellow. So Ilya's research covers binaries as sources of gravitational waves in the broadest sense, common envelopes, merging stellar mass binaries, chemical homogeneous evolution, thermodynamic population synthesis of double neutron star, black hole, black hole binaries, gravitational wave source parameter extraction. It has to do with LEGO sources, signals, and searches. He's your man. And today he'll tell us about black holes and binaries. So, good.
Thank you very much for that wonderful introduction, Sterl. And indeed, I'm having some palpitations because I think the last time I gave a talk in this building was indeed at my PhD defense. Now, I have a vague recollection, most of the PhD defense I tried to blot out. I have a vague recollection of Sterl somewhere towards the end of it saying that it was one of the worst theses he had seen in the history of Caltech. I convinced myself successfully over the years that he was referring to the formatting of the thesis, because I basically took some paper and stapled them together the last possible week, before I could, and then disappeared for 2 weeks of hiking in Yosemite and barely made it back in time for my defense. Now, that may not be the reason that Sterl actually had in mind, but please don't disabuse me of my views. In any case, it's great to be back here, and indeed, I'll try to talk a little bit about some of the very exciting results recently in black hole binaries in a relatively broad sense. I won't just focus on gravitational wave sources, but also mention a little bit about X-ray binaries and so on. And roughly, I'll try to split this talk into 3 parts. So in the first part, I'll talk a little bit about some of the observations, keeping in mind this is a physics colloquium, and I realize that not everybody is necessarily up to date in all of the exciting astronomical observations in this area. Then about a third of it, I'll talk a little bit about some of the work that has been done broadly in this community, including in part by my collaborators on how binary black holes in particular might form, how most of these LIGO sources have come into being. And then the last third, I'll try to discuss some of the new things that we've been doing over the last few years in my group or with close collaborators. But if you have any questions, feel free to interrupt. I don't mind if I don't get through every slide. That's absolutely fine. So one of my collaborators is Arash Rahman, an X-ray observer at Curtin University in Western Australia, and Arash made this lovely plot showing how the overall population of stellar mass black holes has been growing over time. Of course, it started out with observations of X-ray binaries, so black holes accreting gas from companion stars and growing in the process and radiating in X-rays from the accretion disks as a result of this accretion. And then, of course, starting with 2015, there we have observations of gravitational wave sources, and they are quickly picking up as one of the dominant sources of observations there. And we now know roughly as many black holes through gravitational wave sources as we do reasonably confident black holes in X-ray binaries. It's worth saying that in some cases we're not sure whether the complex objects in X-ray binaries are nucleus of the black holes. So you might debate with Arash about exactly how many objects he has put into this blue category. You might also debate some of the things that are in this big category, which are the discoveries of black holes that are not necessarily accreting, or at least not actively accreting, in large surveys. I'll mention more on that in a moment, but basically think of detached binaries, and you might imagine, for example, that you're seeing stars, companion stars, not the black hole is not gaining mass from them, but the stars are moving in an orbit around the black hole, and you might be able to, in various ways, see signatures of that movement, either astrometrically or perhaps if the binary is close enough through so-called ellipsoidal variations, because you might be able to see that as the star is tightly distorted by the black hole, you might start seeing that depending on where this binary is in its orbit and where you as the observer are, you're seeing different sides of the star that have different luminosities. And so you might see this periodic variation in the appearance of the star. Here's a little animation specifically for binary black holes, courtesy of another collaborator called Brockhart at Harvard. Now, up to 2020, these things were real. Beyond that is our projections, of course, of what you might see with future instruments. So these little panels here correspond to LIGO, Advanced LIGO and Virgo observing ground 1, 2, 3, the future observing ground 4, and then various planned future runs with all the way to the end. You're looking at things like Cosmic Explorer and Einstein Telescope, right? And you can see how these numbers are hugely increasing. By the way, over here on the bottom, you're seeing in blue and orange neutron star black hole binaries and binary neutron stars. Of course, many of these things, the exact values, of course, are very uncertain, both because we don't know the merger rates perfectly, but also we don't know exactly how sensitive these detectors are going to be. But just looking at this plot, and of course, the scale is changing because otherwise you wouldn't be able to see anything up through 2020. But it's giving you at least an idea of how exciting the developments in this field are, and maybe motivating why. Well, you're already here, so I don't need to motivate why you should come to this talk, but maybe motivating why I'm excited about some of the work that we're doing in trying to understand these sources. So you've all seen this plot before, so I'm not going to dwell on it in particular, but remember that this is the plot of the sources that LIGO has observed. In orange are neutron stars and blue are the black holes. The reason you're seeing these arrows is these are merger products. So, for example, over here you see two black holes of masses, if you look across, let's say 30 and almost 50 solar masses, merging to make something that's about 80 solar masses, right? So that's how you should interpret this plot. In sort of this magenta color over here, you're seeing relatively well measured black hole masses in X-ray binaries. In yellow on the bottom, you're seeing the masses of neutron stars, mostly coming from radio pulsar observations. The reason I circled a few things over here is just to highlight a few of the issues that you might notice when looking at this plot. So issue number one over here, the idea is, look, there seems to be a difference between the kinds of black holes we're seeing in X-ray binaries and the black hole masses we're seeing with LIGO. Now, some of that you might attribute to selection effects. For example, LIGO is more sensitive to more massive black holes. Roughly speaking, the volume in which you can survey a comparable mass binary scales as the mass to the power of 2.5, at least at local distances where you don't have to worry about cosmological effects. So more massive things are easier to see, but that's probably not the entire story here. Maybe part of the story is that with LIGO, you're typically able to see things much further, and so you're able to probe black holes that formed in the distant universe at very low metallicities, where they might be able to grow to higher masses. But even that probably isn't the full story. So we'll maybe talk about a little bit more about what other parts of the story this might be pointing to. Another issue is over here, these relatively massive black holes, they kind of live in a place where at least some theoretical models tell us that black holes shouldn't exist. So this is a theoretical mass gap, which observationally is not being confirmed. So that's a puzzle. The reason these things aren't supposed to exist is that stars with these very massive cores are supposed to completely explode in what are called pair instability supernova, not leaving behind any remnant. Something is happening there. So somehow either our understanding of pair instability supernova is flawed, or maybe these black holes are forming through other means. For example, they might be, rather than being formed directly from stellar collapse, they might be formed dynamically in dynamical environments rather. So these things might already be merger products of mergers with two other black holes, where those two black holes, having merged, now merge again, and that way you can build up to things that are in this what's supposed to be a mass gap, except it's not. Or maybe something else is happening. Maybe some of these black holes are able to accrete quite a bit of mass after they're born. Maybe they exist in AGN disks where there's lots of gas around and they're able to grow. In any case, there's no questions there. Over here, it's a different kind of question. This is a putative observational gap. In fact, it's not clear at all that there should be a gap there. At least plenty of supernova modelers don't seem to naturally end up with a gap in their distribution of remnant masses following supernova. And yet somehow there seem to be very few sources, very few X-ray binaries in this regime between roughly 2 and 5 solar masses. So maybe there's something else happening there, some other kind of selection effect is preventing us from observing these systems, or maybe these black holes exist, but just don't exist in X-ray binaries where we can measure mass as well. So these are at least some of the questions we might ask after seeing this plot. Spins are another interesting challenge. So here are a few plots. They all, just for fun, I chose the same parameter for all of them. It's a parameter called chi effective. I should have written down the formula, but I'll just say it in words. So chi effective is a kind of mass average spin component in the direction of the orbital angular momentum. So the chi is the dimensional spin of the black hole. So it's the angular momentum of the black hole in units of mass squared, where G equals C equals 1. And if you take the mass of one black hole, multiply it by its spin component in the direction of the orbital angular momentum, add to it the same quantity for the other black hole, and divide it by the total mass, you get chi effective. And you can see that there is some disagreement between people analyzing the same data, even about what is the distribution of chi effective values, for example. So here is a catalog of LIGO observations where you're seeing this rather broad distribution, but with the preference at positive values, but close to 0. Javier, who is in the audience, wrote this nice paper a couple of years ago, where he argued that, well, actually, this is maybe consistent with although there's a spread in the individual observations, many of these observations are only a couple of sigma away from 0. And so really, up to measurement uncertainties, they could really be all consistent with 0 in principle. And so maybe this spread between, all of these events are really consistent with being near 0. And then there's just some extra tail of events with clearly positive chi effective. That motivated a model by one of the Monash grad students. I was involved in this project where Shanika has argued that, well, maybe there's really a population of things, maybe 80% or 60%, we're not entirely sure what the number is, of LIGO objects are really black holes that have no spin at all. And then there's some kind of a tail at higher values of spin, and they're all roughly positive there, but and aligned with overlaying their momentum. I still think that that might be a possible explanation. Other people don't necessarily agree, but I'll at least try to justify why this might be a possible explanation from an astrophysical evolutionary perspective in a moment. But people have also argued that maybe there are some interesting correlations, for example, with the mass ratio parameter, or maybe with some of the other parameters, such as total mass of the black holes. So I think this is ongoing work in progress. Of course, it's not all about LIGO observations. There are also observations of X-ray binaries, in particular, that I mentioned earlier. So here's one that I was sort of involved in as one of the theorists in this primarily observation-led paper by James Miller-Jones. And so what James had done is he looked at Cygnus X1, which is actually a very well-known black hole X-ray binary. In fact, it's arguably the first convincing observation of a black hole. It was, some of you may remember, that it was a subject of a bet between Stephen Hawking and Thorne about whether black holes really existed, and this was sort of their likely bet candidate for the most likely black hole. And I think it's pretty clear that Kip won this particular bet. It really is a black hole. I don't think there are too many questions about that now. But it turns out there were some pretty big questions about what are the actual parameters of the system. So until this paper, people thought it was about a 15 solar mass black hole with a roughly similar companion mass. Turns out that was largely due to a flawed estimate of the distance to the source, which is degenerate with other parameters. And James had done very long baseline interferometry to really pinpoint the distance to the source, and that changed the property significantly. So it actually turns out that it's about a 21 solar mass black hole with about a 40 solar mass companion. Sorry, I didn't had to cut out part of the table that actually showed the errors. So apologies. This is just the median value. Of course, there are significant error bars in all of these, but not too significant. This is plus minus a solar mass, so it's plus minus a couple of solar masses. The other two things that are worth pointing out on this one is the eccentricity is very low. Also, although this wasn't part of the measurement, the total velocity of the system on the sky is very low. It's only moving at about 10 kilometers per second relative to exposed Cygnus OB3. Those two things taken together already tell us that almost certainly the black hole formed through complete fallback. There was not a natal kick, there wasn't a Blau kick, there was almost no mass ejection during the formation of this black hole. So that's already very interesting. The companion star is co-rotating with the orbit. Okay, that you would expect, it's tightly locked because it's almost completely filling its rough lobe. So it's 96+% rough lobe filling. Actually, this is in somewhat weird units. In sort of more physical units, I would say it's more than 99% rough lobe filling, depending on how you exactly define this rough lobe filling factor. And what that basically is telling us is that the star here is not quite rough lobe overflowing. It's a wind-fed binary. So the reason you're seeing the X-rays is that winds from the optical companion are being captured by the black hole and they're feeding onto the black hole, but it's almost there at rough lobe overflow. And that's actually another puzzle I'll mention in a moment, that there's something very interesting happening, that the black hole X-ray binaries we see are almost all in this regime of being nearly rough lobe filling. And while there's some increase in the efficiency of accretion on as the two stars are closer together, that's not quite enough to explain why the systems are almost all black hole filling. So that's actually an interesting puzzle that I think we've resolved a couple of years ago. We, of course, also from the black hole X-ray binaries can learn something about their spins, although with big uncertainties and big question marks. But one of the interesting things is that, for example, the high mass X-ray binaries like M33X7, like LMC-X1, like Cygnus X1 are all appear to be very rapidly spinning. Now, that may very well be because the spin measurements are very uncertain. You're fitting models of either what you think the continuum flux from the disk should be or of reflection lines, iron alpha lines in the disk, or in some cases quasi-periodic oscillators, but all of those things have significant model uncertainties. So one should be very careful about these measurements. But that said, there is something interesting about the fact that high mass X2 binaries in particular appear to be very rapidly spinning, because you might very quickly ask yourself, well, how can you actually end up with a rapidly spinning black hole unless it's born rapidly spinning? Well, you might say it's easy. You just accrete some mass onto it. Mass carries with it angular momentum. As you accrete mass, you spin up a black hole because spin is just angular momentum, right? That's all well and good. Turns out you need to roughly double the mass of the black hole to bring a non-spinning black hole up to nearly maximum spin. Now, if our black holes are anywhere close to Eddington limited, and the Eddington limit is basically a statement that as you're accreting, you're liberating energy, and when you liberate energy, that energy comes out as radiation, and radiation pushes out in the gas, and at some point, if you're accreting too fast, you push out in the gas so hard that you can't accrete anymore, you send the gas out. So that's what the Eddington limit is. And the Eddington limit tells you that it takes order of magnitude 10 to the 8 years, so 100 million years, for a black hole to double its mass. Unfortunately, or fortunately, in a high mass X2 binary, by construction, you don't have that much time. Because if you're looking at something like a 40 solar mass star, this doesn't live for anywhere near as long. It only lives for a few million years. So you cannot, within the lifetime of this binary, accrete enough mass to spin up the black hole. So the argument has to be that somehow these black holes that are already born rapidly spinning, and that's not very easy to do. Ask Jim over here, he can tell you all about how difficult that is. There are some other issues or some other interesting things in observations. The fact that black hole, so this is low mass X2 binaries. So low mass X2 binaries and like high mass X2 binaries are not accreting from winds. They actually have a low mass companion, and you have mass transfer from the low mass companion onto the compact object. If you have mass transfer from a low mass companion, well, it's not that surprising that over the periods are short. They kind of have to be, because if you're transferring mass from a low mass companion has to be pretty close to actually be tidally distorted enough by the black hole to transfer mass to experience what's called the Rostov overflow, which is really tidal gravitational pull being strong enough to rip material off of the stellar companion onto the black hole. But if you're that close together, that must inevitably mean that the system experienced a previous episode of mass transfer from the progenitor of the neutron star or black hole onto this low mass companion. Because at some point, the progenitor of a neutron star or black hole was hundreds of solar radii in size, most likely. And so surely if this binary is very compact now, then it must have meant that at some point you had mass transfer going from the neutron star compact object's progenitor onto the low mass companion. Now, that mass transfer is actually kind of difficult to understand how the binary survives. Because if I transfer mass from a heavy star onto a light star, then conservation of angular momentum tells me that generally speaking, that brings the binary closer together. And of course, if I bring the binary closer together, I want to transfer even more mass. And so it's a runaway process. And this kind of runaway mass transfer leads to a dynamical instability that's sometimes referred to as a common envelope event, because the companion ends up spiraling into the envelope of the massive donor. And the best thing we might hope for at that point, is we want to leave this episode with a binary intact, so we can eventually get a low mass X2 binary, is that we can eject this common envelope. But that's actually really hard to do if you have a big massive star with a big heavy envelope and strong gravity pulling on this envelope, and a little puny companion that's, so in this case, you might have a, let's say, a 20 solar mass progenitor star if you want to make a black hole that's kind of almost a minimal mass. So maybe you have a 10 solar mass envelope, and you have maybe a 0.7 solar mass companion spiraling into it, right? Not that easy to see how you would actually survive that, because there isn't a lot of energy in the orbit, and it's not that easy to unbind this envelope, right? So just in a hand-wavy way, you might not even think that these things should exist. There are also some interesting things. So this is for black hole kicks. Now it's very hard to figure out how rapidly a black hole gets kicked, but sometimes because it's hard to see single black holes, but at least sometimes you can observe the velocities of binaries. So I apologize, I realize it's writing is rather small. This says kick velocity, and the units here are, this is 100, this is 200 kilometers per second. So this is a plot from Pichiati's paper in 2019. And the observations suggest that a lot of these low mass binaries sort of maybe have velocities of order, 100, even a couple of 100 kilometers per second. That's also, if true, and there are error bars and all of these things, of course. This is also an interesting challenge for a few reasons. One of which is that how does your binary survive such a big kick? Typically, if you get a big natal kick, you'd better have an orbital velocity at least as large as the natal kick. Otherwise, the binaries get disrupted by the kick. Also, if black holes get kicks this large, routinely, you might ask yourself, how do you even keep black holes in environments like globular clusters, for example, which have escape velocities of only 50 kilometers per second? So, more puzzles. Other black hole observations. Okay, I already mentioned a few observations that are relying on detached binaries. So here's an example of one, in particular from Todd Thompson et al. From 2019. So this is one of the first detached binaries that, at least with confidence, observed to have a compact object. Whether a compact object is actually a black hole or not is possibly a matter of some debate. But the argument is that maybe this is a so-called mass gap black hole. So somewhere between a maximum neutron star mass observing a couple of solar masses, and where we think, I wouldn't actually believe this particular label of minimum black hole mass theory. I don't know what Todd had in mind when he decided that black holes have a minimal theoretical mass. I don't think they do, but at least these are the typical masses that we see around 4 or 5 solar masses in typical masses in low mass X-ray binaries. So maybe there's this is a gap filling object. There is actually one way you can see single black holes. I think that may be one of the very few ways of doing it, and that's microlensing. So the idea behind microlensing is that you can stare for a long time at a bunch of perfectly normal stars. Let's say in this case, the data are coming from OGLE, which is mostly staring at stars with the galactic bulge. And you stare for a while at the star, and this star is just sitting along, shining nicely at the same luminosity for 30 years, and then suddenly it does this. So here's the stellar magnitude, so this is luminosity. You see that over time scales of 100 days, there's an appreciable rise in luminosity. In this case, something like 1 unit in magnitude, and then a similar decay after another 100 days or so. And you ask, well, what could have possibly made the star do something this crazy after it was sitting there quietly for a while? And it turns out that one of the things that could do it is if another star passes in front of it. Because when another star passes, so I'm the distant star, there's another star that passes in front of me. Of course, this star is gravitationally lensing the light. And this gravitational lens light means that you're capturing a bigger solid angle of radiation from the distant star, and so it looks to be brighter. And in many cases, you actually see this star moving along because you see the star entering from one side of your image and exiting on the other side in a similar time scale, so you know what's responsible for the lensing, and it's all nice and good. But sometimes you see this lensing event and you don't see any admixture of light from another star. And yet you measure from the duration of the transit, you can basically get the size of the Einstein ring, and if you know something about the velocity of the relative velocity of the lens and the source, and then you say, look, this thing should have been at least 5 or so solar masses, or a few solar masses, and we should have seen it. We can see stars that are definitely with a survey that are a couple of solar masses yet, and we didn't see it, and so therefore it must be a dark object, a dark lens, and well, in this case, the only plausible answer could be a neutron star or a black hole if it's massive enough. And so this is one way in which you might, of course, the measurements aren't very certain, and there are big uncertainties, including because of the degeneracy between the relative motion of the lens in the source and the mass of the lens, but this actually suggests that perhaps there is no obvious evidence for a mass gap between neutron stars and black holes, or the black holes are moving rather more quickly than we thought.
Ilya,
Yes.
Can you spell that point out again? Are you saying that when you do these lensing surveys, these micro lensing surveys, that you find lots of black holes of small masses?
Right. So of course you see that look at the sizes of this uncertainties. This is a mass space, right? So you can see that the masses aren't very well measured, but you sort of you look at this by eye and you say, look, there's no gap there, right? And we tried in this paper with Wukovsky to go probe a little bit more deeply and do a little bit of statistics in this, and we concluded that there's no evidence at all for a mass gap. In fact, quite the opposite, that there's strong evidence for continuous mass distribution. But I want to warn you about one caveat, which is that there is the thing you measure most well is the duration of the transit. And duration of the transit depends on two things. One, how big the Einstein ring radius is, right? Which is just a statement about the mass of the lens. So more massive lenses, you expect longer transients, all things being equal, less massive lenses, shorter transients. But now imagine I have a massive lens that is moving really fast. Okay, then it zooms across, and then I end up with a relatively short transient again, right? So if I have a short transient, it could be because it's a relatively low mass lens, or it could be a massive lens that's moving very quickly. And so if I imagine instead that I have lots of in principle these could all be tensor mass black holes that are just whizzing by really fast, right? Now for various reasons we don't think that's the case, but what you really want in order to grade the degeneracy is astrometric measurements, which can provide more information than just this light curve. Ogle alone can do that. There's so far one system for which that has been done, where there were, in addition to an Ogle observation or a similar observation, microlensing event, there was a Hubble observation that allowed you to get much better constraints. And in that case, there were measurements, independent measurements of the mass and velocity, but okay, that was just one system. And that was actually not in the mass gap.
Allow an experimentalist to ask a stupid question here. If there's no mass gap, does that leave room for the possibility of some neutron stars being more massive than some black holes?
That's a really good question. And I'm not sure that we, strictly speaking, can answer that, because in principle, the question is, how do you make a black hole in the first place, right? So for example, some people have even suggested there may be things called primordial black holes that are not a consequence of any astrophysical process, but they are formed because of some overdensities in the initial energy distribution in the universe, and these overdensities collapse into a black hole. And in that case, well, you could have black holes in principle of any shape and size. You might have planet mass black holes in principle, right? Now, in an astrophysical configuration, I think it's a little bit tricky to see how there will be significant overlap between the mass distributions, because generally speaking, we tend to think that these things are born as an end product of the evolution of massive stars, and there's some supernova explosion at the end of it, and depending on how much mass is left behind, the question is, can that amount of mass be supported by the degeneracy pressure? If it can, it's a neutron star. If it can't, it collapses into a black hole. So there's, depending on whatever the true equation of the state of the universe is, which we don't, of neutron stars, which we don't know, there's probably some upper limit for non-rotating neutron stars, which is maybe 2.1 to 2.3 solar masses, somewhere in that range, probably. And probably things more massive than that end up collapsing into black holes. So I would guess it's probably, for astrophysical black holes, it's probably not a significant overlap, but it is conceivable that there's some other process of making black holes that could naturally make lower mass black holes. So this is sort of just a combination of all of these things. So microlensing events, ellipsoidal variations in the light curves, astroseismic measurements by things like Gaia, looking at stars wobbling around black holes in detached binaries, X-ray binaries, gravitational wave sources, and you see that, well, yeah, maybe there isn't, this lower mass gap doesn't really exist. There seem to be now a few objects that seem to be populating it, and maybe the upper mass gap doesn't really exist either. So at least, observationally, I would say at the moment, the indications are against either mass gap existence. Now, I'll suggest a, given how much time I spent talking about binary black holes, a rather remarkable statement, which is that binary black holes shouldn't merge at all. Well, at least as a result of isolated binary evolution. Why is that? Well, we can rather simply ask the question of how long it takes a given binary black hole to merge. And that's really just a statement about the masses and the separations. It's a very straightforward calculation to make. Peters did it in 1964, and we're still using the results of that. And here, just one plot of those results. Focus for the moment on the eccentricity equals 0 line, the blue line. Eccentricity does play a role. But if you look at this blue line, it tells you what, for a given mass, for an equal mass binary, what is the largest separation you can have in order to still have a merger within the age of the universe. Within the current age of the universe, right? Because, okay, if we want to see the merger, assuming those binaries formed after the Big Bang, we'd better have them merge through gravitational emission within the age of the universe, right? And the answer is that if you're looking, for example, for, let's say, the first gravitational wave event observed by LIGO at about 30 solar mass black holes, so the answer comes in at something like 40 or 50 solar radii, about a quarter of an astronomical unit. Then you ask yourself, how much do you expect stars to expand during their life? So stars start out in the zero age main sequence over here in the blue line, and then as a result of during different evolutionary phases, they expand. Again, ignore all of the details. The point simply is that if you look at the kinds of stars that are going to make you 30 solar mass black holes, they'll start out being more massive than 30 solar masses, right? We expect that at some point in their life, they expand to be beyond perhaps 1,000 solar radii. Now, you can argue whether they really do that or not. Maybe they don't quite expand to be that large, but they certainly expand to be far larger than they would be allowed to be in order to merge within the age of the universe, which is shown by this black line. In fact, this black line is telling you that if you apply the sort of typical assumptions about how much mass these black holes might just lose, or these stars might lose in winds, and how big their core masses are, and therefore what kind of a, if you just let the star alone without any interactions, what mass of a black hole would form, then this is telling you that the black holes any closer than this black dashed line over here would already have to would already overflow the Roche globes. In other words, would basically end up interacting with each other and perhaps merging. Therefore, generators would end up merging, right? So this is basically telling us this line is actually below the blue line. It tells us that even with no expansion past zero age main sequence, you should never form merging black holes. Well, the star should first interact and presumably merge in the process, right? It's actually not that easy to form merging binary black holes. And so, of course, that's not the case because, I know this is illegible, don't worry. I just wanted to show that this is from a review that we've written with Flor Brokarten in Living in Relativity last year, and some of the other plots I'm showing are from a review with Alison Farmer, also finally published last year, although written a few years ago. This is more or less my excuse for why I'm not going to have too many references in the next slides, because you can see the huge numbers of references in this review alone for different information channels for binary black holes and different predictions for the local merger rates from theory, and the observations are rather few and far between over there. Those are the orange lines. Everything else in this case is theory. So I'm not going to go through and mention every single one of these models and observations. I'll just try to lay out the general story, and apologies if I'm not citing something that you worked on. It's not out of ignorance, it's probably somewhere hidden in the multiple hundreds of references in these reviews, so excuse me for not mentioning it. So how do they merge? Well, I'll try to talk briefly through these three possible channels. There are many more available. Channel one, isolated binary evolution. So what happens here? What happens here is you start out with two stars at birth, and you actually typically put them pretty far away from each other. And then you hope that somehow they come closer together just at the right moment when they can, when it's already allowed, and when they will be able to merge as compact objects. So what it might require is an episode of mass transfer from one star to the other. This mass transfer episode might even widen the binary a little bit, that's fine. The primary, the initially more massive star, collapsed into a compact object, let's say a black hole. Then the secondary engages, expands at the ends of it, as it's evolving off the main sequence, stars expand, and eventually it starts transferring mass onto this black hole or neutron star. Now, maybe this mass transfer is a dynamically unstable process, and you end up with a common envelope you eventually eject, and that takes a lot of your orbital energy, and that allows you to bring the binary closer together. Maybe it's just a more extreme mass ratio in this case, so maybe your secondary here gained a lot of mass while your primary lost a lot of mass. So now you end up with a situation where this star is actually, even though it started out being less massive, it's now a lot more massive than this one, and transferring mass from heavy to light brings the binary closer together. In any case, you bring the stars closer together at a point where this one is already a compact object, and this one is maybe the naked helium core of an evolved star. And at that point, it's also quite small in radius, quite small in size, so you can afford bringing these close together. And then finally, they can go on to merge through gravitational wave emission after the second star also collapses into a compact object. And if you try to very crudely ask yourself, well, what might the event rate be? Of course, there are lots of models, population synthesis models, for example. My group has one of our own called Compass. Plenty of other groups have their own models, and you've seen the many predictions over there. So I'm not going to try to argue for which one is better. But it goes something like this, right? You might ask yourself, okay, well, if I want to make a binary black hole, what fraction of all binaries might go on to make binary black holes? Well, maybe roughly 1 out of 1,000 stars, if sampled from the initial mass function, is massive enough to make a black hole, meaning 20 solar masses or more. Now, typically the masses of companions are not distributed again according to the initial mass function. There's a correlation, and in fact, maybe the companion masses, the mass ratio at birth for binary is actually more uniform. So if you have a massive primary, then the secondary maybe is fairly massive too. So maybe half of them go on to be massive enough to also form black holes. Okay, the initial separation, well, it has to be in roughly the right separation range, but that's maybe actually not all that constraining, because if you imagine that binaries are roughly uniformly separated in the logarithm of the separation, so uniform in the log, which seems to be the case, there's actually a pretty broad range of separations, initial separations, that might be good enough to allow you to have this kind of evolution. So that may be a reasonably large number, like point few. Surviving the first supernova. Well, okay, you've got to survive the first supernova, but okay, black hole, that means not too many binaries should be disrupted by the first supernova. For neutron star binaries, that's not trivial, because neutron stars can get pretty large kicks. Black holes, maybe they tend to get smaller kicks. We see from Cygnus X1 at least that relatively massive black holes seem to maybe not get much of a kick at all. So let's actually set this close to 1. The common envelope one, well, I wrote common envelope here. I'm not even sure that I believe anymore that binary black holes are forming through a common envelope. Maybe more than that. Maybe there won't be time to do more than that, but we'll see. There may be at least some fraction of, and I'm going to rather politely, without explaining why, claim that it's order of 10% for things that might survive this common envelope phase and bring you close enough together. Okay, again, order unity of binaries that survive the second, or of systems that survive the second supernova, and then maybe 20% are close enough to actually merge with the nature of the universe. That requires, of course, that you end up close enough after this second episode of mass transfer, and also that your winds don't widen the binary too much. And so if you do this roughly, you end up with something like a few in a million binaries might be able to do this. Then you say, okay, well, there's the star formation rate is something like 0.01 solar masses per cubic megaparsec per year. In other words, there's a galaxy like ours, like a Milky Way, one in every roughly 100 cubic megaparsecs, and forming maybe a couple of stars per year. Then you multiply that by typical binary mass, which is a quarter a solar mass, and you multiply it by this yield fraction of 5 in a million, and you end up with something like 50 per cubic gigaparsec per year, which is roughly where LIGO is observing the merger rate of binary black holes to be. So, okay, so maybe not that crazy, at least from Ray's perspective. Now, there's a variation on this channel, which I won't spend much time on, but I'll mention it because it's near and dear to my heart. So this is something that a few people, including Selma Demick and myself, had worked out a few years ago as a possibility. Again, not at all convinced that it's a real thing. It's called chemical homogeneous solution. The idea is that, where's my magic wand? Here's my magic wand. Stars, thou shalt not expand. Okay, great. I wave my magic wand. That explains chemical homogeneous solution. So if stars don't expand, life is great. I start with two stars close together. They never expand. Oh, and by the way, I also do something else that's crazy along with in my magic wand. Stars, thou shalt convert all of your hydrogen into helium. That also helps because most stars, okay, it's the reason they expand. They convert hydrogen into helium in their cores, and then they have a big fluffy envelope of hydrogen left over. Helium cores contract, hydrogen envelopes expand. You start with all this mass transfer nonsense, which you don't fully understand. Things are difficult. If only the stars didn't expand, and also they converted all of their hydrogen to helium, which goes along with not expanding, then life becomes really simple, because then you end up with in place closed binaries that are already very massive, right? Because if you convert all their hydrogen to helium, you can end up with obviously a much heavier core for a given initial mass. So you end up with forming more massive black holes. Life is great. Two massive black holes close together. Fantastic. They just merge with gravitational wave emission. Nothing doing. Okay, the only problem is, how do you keep stars from expanding, and how do you convert all the hydrogen to helium? Well, those go hand in hand. You convert all the hydrogen to helium. There's no envelopes, they don't expand. How do you do that? Well, you have to mix within the stars. So here's this little sketch of mixing going on within the stars. And if you mix all the material from hydrogen from the outside into the core, and if you were to fuse into helium and then take that and mix it back out to the outside, you can convert, in principle, all your hydrogen to helium. Again, life is simple. Why might you do that? Well, one possibility is if your binary is very close together, your stars, because they're going to be tightly locked, will end up being very rapidly rotating. If they're very rapidly rotating, then maybe, well, then we know one thing that's going to happen is that there will be a significant temperature gradient across the star. So there will be a big temperature difference between the hot poles and the cool equator. And maybe this temperature gradient is going to be responsible for the creation of neutrino currents, so-called Pennington-Sweet circulation, or other mechanisms of effective mixing. And so maybe that allows you to bring hydrogen from the outside into the center, use it, bring the helium back out. Why am I saying it's not certain? Well, because first of all, stellar rotation and mixing and angular momentum transport in stars are very difficult to model. And secondly, because for a while it looked like there were a few observations of stars that were good candidates for experiencing this process earlier in their evolution, still on the main sequence. But although some of them seem to have the kinds of temperatures and luminosities you would predict if this process was working, they don't seem to have the kinds of abundances that you would expect if this process was working. So I'm not really sure that we have good evidence that this ever really works. Third channel, dynamical formation. So the story here is you just end up with a sea of black holes in some dense environment like a globular cluster. And then you have a kind of dating clock for black holes. So you don't necessarily start in a single binary and then try to merge your black holes that were already formed in the same binary. Instead, you have this sea of people milling around in a bar. Sometimes, some of them might form a binary. Sometimes a rather rude third party will bump in, not caring that these two have started in a binary. Sometimes the third party will actually get ejected because the two black holes that are already there aren't enjoying the interruption. And when that object gets ejected, he or she gets booted out, and of course, in doing that, energy is expanded, so the remaining binary comes a little closer together, and eventually this might continue until the binary gets sufficiently close together that gravitational waves can take over and bring the binary to merger. Now you can do, this is Sterl. I have been paying attention over the years to all of these wonderful tricks. So this is a trick out of Sterl's book. You can do a very crude upper limit here by saying, look, consider a typical globular cluster. It has, let's say, 1 million stars in it. Now, I just said well, roughly 1 in 1,000 stars might go on to make a black hole. So there are at most 1,000 black holes, well, order of 1,000 black holes in this globular cluster. Let's imagine that all of them end up merging, right? And I can even reuse them. So second generation mergers, third generation mergers, etc. Right? Still, I can only have as many mergers as the number of black holes. Okay, technically, number of black holes -1, right? And so if there are 1,000 black holes there, I can have 999 mergers. Now I want to space them out over the life of the universe, which is about 10 billion years. Okay, it would be kind of weird if all of the mergers are happening right now, right? So I might imagine they're spread out over something like the life of the universe. And if there's roughly a globular cluster per cubic megaparsec, I can convert this rate of 1,000 mergers per cubic megaparsec per 10 to the 10 years, and I get an answer like 100 per cubic gigaparsec per year. Now that's a pretty large number. It's larger than what I had in the previous slide, but I don't necessarily believe this number. And one easy way to see why is that even if this process is very efficient, it typically, to get a single merger, requires many injections. The way to think about that is that the typical velocity, orbital velocity you need in order for gravitational waves to take over is close to 500 kilometers per second. And that's actually pretty weakly dependent on the masses involved because of the scaling of the merger time scale with mass and separation. And so this is, this sort of critical velocity on the scale is something like mass to the 1/8 power. So it really is in the range of a few hundred kilometers per second. The escape velocity from a cluster is only about 50 kilometers per second. So that means that when we have this interaction and we give a significant fraction of the orbital energy to the interloper, to the ejected object, that means the interloper is leaving with a velocity of order the current orbital velocity of the binary. And so that means that to go from the 50 kilometer per second binary to 500 kilometer per second binary, we need to kick out a nice handful of black holes, right? And so this is sort of a very simple argument to say that at least probably a factor of 10 should be removed from that 100 from the number of 100 cubic gigaparsec per year. Okay, I've realized that my plan to give you a third part of the talk has completely failed because I've spoken way too slowly, so I apologize for that. So I'm going to skip a couple of slides and go straight to the end. And if people are interested, I can afterwards share some of the more recent work we've been doing. So apologies, this ended up being mostly review. But I meant to give a summary at the end. Instead, I will, by way of a summary, I'll show a couple of bets. So the summary is a few result bets. So this was a very sad bet, although I was very happy to win this bet with Kip, but you can see Kip was very sad too. He wrote with great sadness, I hereby concede. This was a bet about whether or not we had already seen a binary merger in 2010. Some of you may remember something called the big dog. Well, the big dog was a blind injection, so we didn't see one back then. That's fine. At least we've seen them now, so that's all done and dusted. Then I had this bet with Neil Kander that at least one of the first 10 complex binary coincidences as claimed by the Lyckenberg collaboration will be accompanied by a clearly identified electromagnetic counterpart. That bet I lost, but I was very happy to lose it because that meant we had observed GW 170817, which was a double neutron star merger with amazing electromagnetic counterparts associated with it. So that was absolutely fantastic. And I still think I was right to make that bet because as the next 90 didn't have any counterparts. So there was this one. I actually wasn't a participating party in the bet. I was the arbiter for this bet, but this was a bet about whether the high mass gap that was postulated to exist because of parent stability supernova actually would exist or not, and it turns out it's filled in. So these are all result bets, but there are plenty of others coming up. So there's a bet, for example, in the nature of mass gap objects. So I didn't get a chance to tell you about where I think about mass gap objects, but I think you may have the lower mass gap objects between 2 and 5 solar masses. But I think you've already got the message. I don't think there's a mass gap there, and I think there are other very benign explanations for why we don't see low mass density binaries with black holes within the mass gap that very quickly have to do with the fact that those black holes get particularly large kicks, for example, and therefore break up the binaries. So there's a question of whether or not this mass gap will be filled in. There's a question of whether or not we will ever see an eccentric binary black hole in the LIGO band. Now that would probably be a telltale sign of dynamic information because gravitational waves tend to damp down eccentricity. So if you see something that's eccentric at the very high frequencies, very close to merger in the LIGO band, you really need to form it already at those very high frequencies, meaning very close separations. And I don't think it's possible through isolated binary evolution. So dynamic information would be the way to go. There's a question of whether we will ever see gravitational waves from a supernova. So lots of really exciting things in this field, and hopefully many more fun discoveries to make. Thank you.
Final bet.
I'm sorry?
In the final bet, when was today? I mean,
Oh, today, this bet was made in December of last year. So December of,
so you have 4 years. To
yeah,
go.
so it was 4 years and 10 months ago. Yeah, this is very soon. Yeah, sorry, I cut off the header.
Okay, questions? No questions. Everybody's.
I tired everybody out. I'm sorry.
Well, I'm gonna ask you about chemical evolution, since that's one of your projects. It sounds like you no longer believe it. And I've also heard people claim that it's already been ruled out for other reasons, related reasons, but I don't remember what those reasons are, so I'm asking.
So there are, I'm still open to the possibility. I think actually, if you do it in the way that we had initially argued, we've sort of followed up in some more detailed calculations led by my physician Jeff Riley, and we actually find that in our original framework, we would actually be producing too many chemically homogeneous evolving binaries to be consistent with like observations. So there would be far too many high mass systems. The observational evidence for chemically homogeneous evolution, as I mentioned, is from stellar observations, is very uncertain. I don't think this completely rules out the possibility of chemically homogeneous evolution, but it might mean, for example, that it's a less common thing, and that some of the models that we were using, for example, coming from MESA stellar models that suggest what might be the threshold for chemically homogeneous evolution in terms of stellar rotation might have been too optimistic, and in fact the threshold might be higher. I don't think we can actually rule out chemically homogeneous evolution. It might just mean that it's a less common thing than we initially thought.
So in the dynamical channel, I guess there's the question of how long the binary black holes actually stay in the black hole. I mean, so obviously the final merger, if it gets more than 500 or 600, you can have a merger, but that may also kick it out of the black hole. But even before you get then, you're already sort of starting to worry at 200, if they're equal mass, they're being ejected, and so they don't have all the mergers.
I guess so. What? But it depends on the mass spectrum. So for the black holes that we actually see, LIGO, that you would like, do you think you can have very many forming in that channel?
So I think, I mean, one possibility, of course, is that they might be, this channel might still be operating, but in an environment with higher state velocity. So for example, nuclear clusters. So people recently have been pushing hard for the possibility that nuclear clusters, and especially those with AGN disks, might be a very plausible channel because, first of all, they are these state velocities at 500 kilometers per second, for example. So, that's less of a problem. Secondly, your black holes can grow if they accrete mass from the disk. And thirdly, that they're possibly, although I think there are big question marks on this, you might have some kind of migration traps in the AGN disk. So you might actually convince the black holes to sort of all gather in the same places, and that might enhance your merger rates. I think there are a lot of things that are still very open to debate on all of those topics. Well, not the escape velocity, that part is clear enough, but things like how many black holes you actually have, how many stars you even have in those inner regions, and especially massive stars. How efficient is mass segregation? How efficient are the migration traps, etc.? Can you really grow the black hole mass accretion? All of those things I think are still open to debate, but at least potentially, that might be one way to get out of this problem.
Yep, Jim.
So can you explain why you don't believe in the lower mass gap? Because theoretically, I think it's very natural to expect that to exist. You need a star with a massive enough core in order to form a black hole. And the whole core falls into a black hole, so you need it to be these 5 solar masses. So why don't you believe that?
Well, so these are, so if you look at, thank you for giving me a chance to show an extra plot. So if you look at the pluses here on this plot, these are coming from Bernard Muller's models. So this is from a paper with my collaborator Bernard Muller, who is a supernova modeler. Now this is actually, it's a little bit funny because it's sort of a combination of his proper 3D models and simplified 1D models that are inspired by his 3D models. But at least in these models, right, Bernard is arguing that there is a lot of stochasticity. So if you look at the carbon oxygen core mass, you will see that here it's not a simple story where, depending on the carbon oxygen core mass, you have either complete fallback and the formation of a massive black hole, or a supernova explosion leading behind a neutron star. You actually have 3 regimes. Things that are along the roughly diagonal here are things that experience complete fallback, no explosion at all. Things that are over here are sort of your classical supernova leaving behind a neutron star, and the various pluses that are in between are things that experience partial supernova, but also have significant amounts of fallback, leading to black holes, and these things are sitting very much in the mass gap. With Bernard, what we did was we tried to say, okay, let's create some recipes for the that are sort of stochastic probabilistic recipes for the remnant mass based on the carbon oxygen core mass. Those are the points here. Okay, we didn't try to reproduce all the fine features because we don't believe all the fine features, but maybe again, you have these 3 possibilities, stuff in the middle, stuff over here, and if you apply that to single stars, this kind of prescription, you end up with maybe a relative paucity of objects in the 4 solar mass range, but certainly not their absence. But there's a more important part of the story, which is that as part of the story, we looked at natal kicks as well. And one thing that kind of bothers me about most population synthesis models, for example, because of course we're talking about measuring the black hole mass or neutron star mass, right? Most of the time we're doing it in binaries. You want dynamical mass measurements. Most of the time people just say that there is some distribution, let's say of measured pulsar velocities. You go out and you measure a bunch of pulsars and you get something like, and you fit it to, let's say, the Hobbes-Maxwellian, right, is a typical fit that people make. And then they say, okay, well, any given neutron star is randomly chosen from the distribution. I think that's a bit strange because surely the kick has to match up to the properties of the progenitor star at the moment of the explosion. I mean, there has to be some physical connection. It's odd to me to assume that you are randomly choosing from a distribution. It's sort of like saying that, okay, you plot all the distribution of all of the heights of people out here, and then you say, okay, well, Bobby here is an NBM player. Okay, we'll pick his height randomly from from the overall population distribution, because that's a distribution we know, right? There are selection, you know more about these systems, right? And in particular, you can come up with a reasonable model again based on Burnet's simulations of what a typical kick might be that's going to be meant preserving. That depends on how much mass is actually lost in the explosion and how much mass is left behind. And if you apply that model to the observations, that already does a lot in reducing the masses, the number of black holes in binaries in this mass gap regime, right? So in dash blue is what you would get there with ignoring kicks. In red is what you get there after accounting for kicks, because those low mass things are the ones that get the biggest kicks. Now that alone is enough to explain the absence of things here. That's only part of the story, clearly. That's one part of the story, I think. I think there are a few other parts of the story having to do with binary evolution as well, and in particular the common envelope phase, because I think here the common envelope phase, I think, is critical, as I said earlier, for low mass binaries in particular. And that's one plot I'm not going to show right now because I'm already 5 minutes over time, but I think that's going to be a big part of the story, is understanding exactly what's happening in common envelope. And I think a lot of our intuition for common envelopes based on low mass stars doesn't really apply to high mass stars. And I think we actually do have a proposal. So either chat with me afterwards or look up Rio Hirai's paper from last year, where we spell out this proposal for what might happen in high mass common envelope events.
So last question.
So for the chemical homogeneous channel, is it possible for only one of the two stars to be rapidly rotating? And is it possible to explain like the X-ray binary stop the spin?
So that's a very good question. So the question is, can only one star experience chemically homogeneous evolution? In principle, yes. In practice, it turns out that generally speaking, the window for chemically homogeneous evolution is so narrow that in order to get rapid enough rotation, you basically need the two stars to be in contact already on the main sequence, because if they're any wider than that, the orbital frequency is too low that even if they are tightly locked, they're not going to be rapidly spinning enough for chemically homogeneous evolution. And if they're in contact, then it seems likely that there is mass flow back and forth. And so in many models, the assumption is that actually these stars which are in contact, they actually end up having the same mass, right? They share mass until they basically have the same mass. So, and then once they have the same mass, okay, they're basically evolving in the same way, meaning that if one of them is going to be chemically homogeneously evolving, so will the other one. So at least in the simplest models, I would say that's fairly unlikely. There is maybe a very small sliver of parameter space where it's possible. Pablo Marchand had a paper on that in 2017, but I think that's a very rare outcome, at least as far as we understand the process.
Okay, well, let's thank you. If you have questions.